Good morning. Welcome to Krishna's classroom. We continue with our discussion on the contraction mapping principle and the consequent fundamental theorem, namely the fixed point theorem. And there are several versions of the fixed point theorem, as I pointed out earlier. But we are interested in the most fundamental one. And as I told you, that the theorem became very significant because of its scope for application in the search for solutions, or at least to prove that there exists solutions for certain equations. Again, the maps were not constrained by any special conditions like linearity or any such thing, but even non-linear maps were amenable to the application. Now, I have stated the theorem here. We have already said what contraction mapping is. We shall revisit that. But the theorem that we want to prove is this. There is a vector space, or not a vector space, a metric space X, distance function D, and T is a map from which maps X to Tx. Now we assume that T is a contraction. And T is a contraction automatically means that T is a continuous map. Okay? So that we have already seen in the last lecture. I have made this comment. Now, what we prove now is that there exists a unique fixed point for T, which means that there exists a unique X. There exists a unique Tx equals X. This is what we want to prove. Which means there is exactly one point in X which has not moved under the map T. Okay? So that's the condition. Now let us recall what a contraction map is, because that is very crucial in our arguments. So recall that T is a contraction map. So T is a contraction here. If distance of Ty is less than or equal to c times distance from x to where 0 less than c less than 1. That means there exists a c such that this condition is true for every x, y belonging to x. This is the definition. So what we assume is that T is a contraction. Now we want to assert that T has a unique fixed point. Now how do we get to this fixed point? Now this is the problem. Okay. Now see that if you recall the Picard's approximation theorem to prove the existence of the solution for an initial value problem, y derivative equal to f of xy with the y0 equal to y0. Now recall this and how we approach this problem. The strategy was to convert this problem into an integral equation, something like y minus y0 equal to integral, whatever be the interval, a to so this is y at x. And suppose this problem is on the interval x belonging to some interval ab, then for x belonging to ab. So the first step is to observe that this initial value problem is equivalent to this integral equation. And then what we did was we started with any function, say y x equal to identity equal to y0 for x belonging to AB, and then iterate. The iteration was you had yn x equal to this was the iteration. So we constructed a sequence of functions y and x, and under the conditions of the theorem, which I am not elaborating at the moment, we will take up this problem later, show that this converges to a function yx, and a crude way of, which needs mathematical justification, limit n tending to infinity and which is equal to y0 plus integral 0 to x. There are a lot of steps in between. F t limit n tending to infinity which is equal to y naught, therefore which implies, so this if all these intermediate steps can be justified, I mean that's the main part of analysis that we encounter, the sort of conditions that we have to impose on f to ensure that all these interchange of limiting process with the integration and then later taking it inside the function is justified, and if that is so, such a y would be that the limit of the sequence of functions y and x will be a solution of the integral equation, and therefore since this integral equation is equivalent to the initial value problem that we have started with, the initial value problem has a unique solution. Of course, this is, as I said, this is under conditions on f, things like f is Lipschitz with respect to the variable y, etc., etc. I mean, all those things we are not bothered at the moment, but just for the time being, you take that there are conditions which allow all these, which allows us to justify each one of these steps. I mean, this is the Picard's approximation that we had, which say it is sometime in the 19th century that this problem was addressed. Now, we use this idea. So actually, we make use of this idea, and what we do is just take up the following. What we do is the following. Start with, let x naught be any element of, start with any element x naught here. Then what we do is first map this using t to tx naught, call this x1, then map this further to, this is x2, x1, x2, and so on, and eventually you see that because the mapping is a contraction mapping, it just starts crowding around. Okay, and eventually you get a sequence xn which converges to that. So we will do this. So if tx naught, then we have at least partial proof regarding the existence. Now assume lift naught define x1 equal to tx naught, x2 equal to tx1, and so on, xn equal to t, etc. In this way we produce we obtain a sequence namely so we end up with a sequence of points xn. Now what we claim is this. Xn is a Cauchy sequence. So this is the statement that we first write. And here we make use of the fact that T is a contraction. So let us compute this. So compute this dxn, this is equal to dtxn minus 1 minus 2, and this is less than or equal to and further this is equal to c times e of n minus 3, and which is less than or equal to c square and so on, and so on, and so on, which is less than or equal to eventually less than or equal to c to the power n minus 1 e of small. So this is what we obtain. So what we end up with is that is we have reduced to the points x1 and x0. Now this is the inequality that we are going to make use of. Now we want to work on, so we want to estimate this. This is what we want to estimate. So let us use triangular inequality. So we see that by triangular inequality, is less than or equal to we are assuming n is greater than plus d Now let us use the estimate of the various terms, and you see that this is less than or equal to c to the power m plus c to the power m plus 1 c to the power n minus 1 d of, now that is fixed. Okay, and this you can sum up, that's less than or equal to c to the power m, we are taking m c to the power m d of divided by 1 minus c. That's the analysis that you have, and that's very simple to get this from this. Now we make use of the fact that c lies between 0 and 1. That can be made arbitrarily small by choosing n and m sufficient large. Using this estimate, everything depends on this, because we have assumed this dx1 x0 is not equal to 0. Okay, so we can estimate this, and since c lies between 0 and 1, it follows that this can be made arbitrarily small by choosing n and m sufficiently large. That is the sequence xn now you need the help of completeness of the space to assert that this sequence converges. Now x being complete, so this assumption is very important here. It follows that there exists an x belonging to x such that equal to x. Now use the continuity of t. Every contraction map is a continuous. By the of t and the relation xn equal to txn minus 1 by letting n tend to infinity we have t of thus x is fixed point of fixed point. So we have proved the existence of a fixed point for t under the assumption that t is a contraction and x is a capital X is a complete metric space. Okay. Now what remains? The question that you ask is, I'll make some remarks afterwards. The question that remains is this X uniquely determined? So the question is, unique. That's the question. Now this is quite easy to prove because by contradiction. Okay. So x prime be point of t. Then we have following Tx equal to x and Tx prime equal to x prime. Therefore, let us compute the distance between x and x prime is equal to d of which is less than or equal to c times x and x prime. And c is less than 1. since C is less than 1, it follows that dx x prime is less than x prime, and this is not possible. Just contradiction. Therefore, the fixed point is uniquely determined. So the abstract formulation is very simple. Now, what remarks we can make is that we started with an arbitrarily chosen x naught belonging to x, and then proceeded through the step-by-step approximation. Okay. So that completes the proof of the theorem. So we make some remarks. One can any x naught belonging to, because it will eventually collapse down to this point. Okay. Xn's are close to the fixed point gets last. In fact, one has the following estimate. We have the distance from t to the power n x naught x is less than or equal to this is an estimate that you have. Now, a second remark that we want to make is this: let xd be complete. And we replace the condition that T is a contraction by the following. And suppose F is such that for some positive integer k t to the power k is a contraction. Then t has a now this is also quite easy to prove. Okay. Now these are some of the remarks I want to make at this stage, and later on we shall see how this result is used in proving the existence of solutions of differential equations. And it's because of the enormous prospect of applying this to study the existence of solutions of equations. The theorem is very important. It's very extensively used in proving. Also, many partial differential equations are shown to have solutions in appropriate spaces that the solutions do exist. As we shall see with the initial value problem that the Picard's approximation has been used to establish the solution of an initial value problem for ordinary differential equations. Now the same we shall consider by transforming it into a fixed into a situation where one can apply the fixed point theorem. That means where convert the problem to another operator for which you seek fixed point. Once you establish that it has a fixed point, that fixed point will give you a solution in the appropriate space. Now this we shall discuss in the next lecture. So at this stage we conclude. Thank you very much.